We can solve some few examples here. We have pure inductance of, you see, when they say pure inductance, they mean that this inductor has no resistance. Otherwise, if the inductor is not pure, it can have its resistance too, and it can have reactance, and yet it can have resistance. So it is an inductor that is made in such a way inside there is a resistor. Okay, but this is a pure inductor, so it has no internal resistance, it has only reactance. So a pure inductance of 318 millihenry is connected in series with pure resistor of 75 ohms. The circuit is supplied from 50 Hz source, and the voltage across the 75 ohm resistor is found to be 150 volts. Calculate the supply voltage, the phase angle. The first thing I advise you, when you solve current electricity questions, you are supposed to draw a sketch. It will help you. For instance, we are having a sketch here. The pure inductor of 318 millihenry, it's here, connected in series with pure resistor, it's here. The circuit is applied from 50 Hz source. Voltage across the 75 ohm resistor is found to be 150 volts. Therefore, the first question that you're required to solve is to find the supply voltage. The second question, you're supposed to find the phase angle. We are given voltage across the 75 ohm resistor. We're given the voltage across the 75 ohm resistor. So we proceed as follows. We can either decide to draw our phasor diagram, just a simple illustration. So minus VC. But here we don't have the capacitor, so this value is 0. We only have the voltage across the inductor. So here we have voltage across the resistor. Voltage across the resistor is found to be 150. As we have been told here, voltage across the resistor is found to be 150. So find the supply voltage. The supply voltage can be found as follows. Okay, first, if we agree that if we have the voltage across the inductor, we can get the voltage across the whole circuit, the supply voltage, because we can apply our Pythagoras, we can apply this formula that we have here. Okay, if we have this, then we can get our supply voltage, because this is not present. So our task here can either, one way can either be to find the value of VL0. We know value of VL0, we know that the value of VL is equal to I times capacity, the reactance of the inductor. But we all agree that these things are in series, so whatever current that is passing through the resistor is the same current that passes through the inductor. But we are given the voltage of the resistor, so from the voltage we can get the current. It's what they have done here, that voltage divided by the resistance, you get current. So voltage we are given 150, the resistance we are given 75 ohms. We divide, we get the current is 2 amperes, current of the circuit that is passing through the circuit. Again, we know the reactance of the inductor is given by LW. This L we are given as 318 millihenry, but this angular frequency is 2 pi over period, or in other words 2 pi times frequency. So we are given the frequency as 50 volts, so we can multiply 2 pi times 50 times the inductance 318 millihenry, then we will get our reactance as follows, as they have done here, that 318 millihenry times the angular frequency 2 pi f, we get our reactance as 100 ohms. Maybe a point to remind you that speaking of the reactance is dimensionally has the same units as the units ohms. You see, now that's why I always insist, whenever you give a physics definition, you give the value of qualitatively mentioned statement and the value of the quantitatively statement. The quantitative should at least mention the SI units. The SI units are ohms. All these reactors, the SI units are ohms. It's only that the meaning is different, but the units dimensional is the same. Okay, so from here, if we have XL now and we have the current, we can get the voltage across the inductor. The voltage across the inductor is given by IV times the reactance of the inductor, and we have 200 volts. So from our formula, we know that EV, if we apply Pythagoras, as EV is equal to the square root of VL square plus 150 squared. So from there we can get our supply voltage as 250 volts. Again, the phase angle, whatever value that you decide to use, you can use cosine. As long as you have these values, you can use n. You can decide to use sine, you can decide to use cosine, you can decide to use tan, but eventually you should get your answer. Okay, for instance, here he has decided to use tan, and we know that tan theta is equal to VL over VR. So if we have VL over VR, or we can decide to use resistance as XL over R. XL we got here, XL as 100 ohms. Okay, and the resistance that we have is 75 ohms. So we can get there and find tan inverse. The answer becomes 53.06 degrees, the phase angle. Another example here, we have an inductor has a 54.0 ohms resistance reactance at 60 hertz. What will be the maximum current if this inductor is connected to a 50 hertz source that produces a voltage of 100 volts root mean square voltage? Okay, so we have two conditions here, that we have an inductor that is functioning at 60 hertz, and we have an inductor that is functioning at 50 hertz. So our issue here, what will be the maximum current if this inductor is connected to 50 hertz source that produces a 100 volts root means square? Okay, there are two ways in which we can proceed here. Okay, there are two ways in which we can proceed, because our question here is that finally, when they say maximum, usually when they say maximum means the peak current. Okay, when they say maximum, they usually mean the peak. So peak current, peak voltage, that's what they mean. So our question here is to find the maximum current. So we know that if V is given by IR, okay, if V is given by IR, we can get our peak current if we have the voltage and the resistance, and for this case we have the inductor, which is the reactance. So our first task, because we are given the voltage we are already given, our task is to find the reactance at the new frequency. To find the reactance at the new frequency, because we are looking for the current at the new frequency. So we find the reactance at the new frequency. So there are two ways we can proceed. It's either we first find the inductance of the inductor, because the inductance is given by the reactance divided by the angular frequency. The reactance we are given as 54. The angular frequency is 2 pi f, 2 pi times 60. So we can get our value of inductance as that. Then with this value of inductance, we can use it in the new frequency to get our new reactance, in which we are interested here, because here we are supposed to use the new reactance at 60, and because we are given the voltage at 60, and we will get the current at 60. So after getting that, we can find the reactance at 50 hertz. So we have the inductance times the angular frequency at 50 hertz as 2 pi times F, this time F is 50, and we get our reactance is 44.9. So finally we conclude with the same formula, that to get the peak current at 58 is equal to voltage peak at 50 over XL, the reactance at 50. But we are given the peak, we are given the root mean square voltage, so we need to convert this. Otherwise, if we use that only, we will get the root mean square current, we won't get the peak. So it's either we convert now the voltage into peak so that we get our current into peak, or we use the root mean square voltage to get current, root mean square current, then we will convert that root mean square current to peak current. So here we have just converted first the root mean square voltage, as you remember, is equal to you remember the relation here, the relation between the peak and the root mean square here. So that current, root mean square current, is equal to peak current divided by the value of root 2. Okay, so we have the peak current divided by the value of root 2. So the other way around, you just convert using the same conversions here, and you get the answer is 3.13. Another way, if we couldn't decide to use it here, is here we can use ratios, that if XL is given by LW, then XL in at 60, L at 60, W at 60, divide by XL at 50 over L at 50, W at 50, so that this and this cancel, because it won't, the inductance won't change. So finally we have the XL at 50 is equal to XL at 60 times, because 2 pi and 2 pi will cancel, so we just have frequency at the ratio of the two. So finally we'll get the reactance as 45, just similar to this. Finally we get our answer.